some parametrics, right? Okay, so that one I've taken over to here. So here are our parametric equations for x and y.
Yeah.
dy dx, you know what you always do to find dy dx from parametric equations? You know it's going to be dy dt?
Yeah.
Over?
Oh, is it dt over dx?
Oh, it's times dt over dx, which you can rearrange to just think of, in this case, when you're finding the derivative of, you know, from parametric equations, you just think of it as dy dt over dx dt.
Okay, dx.
I'm not denying that is what you said.
Yeah.
I'm just saying you might as well remember it like that.
Yeah.
So that's going to be dy dt will be what? Do you know the? Yeah. I think a couple of weeks ago we did differentiate tan, didn't we? We talked about going the other way around as well. Do you recall the derivative of tan?
Is it sec squared?
Yes, it is. So 2 tan t will be, of course,
2 sec squared.
Yeah, of t. And now that's over.
That's over would it be cos squared t?
No, that would be a bit naughty. You're saying because the derivative of sine is cos, I'll just have the square of that. No, you've got to think of sine squared as a composite where sine is the inner function.
Yeah.
And of course the outer function is?
Sine is in.
If I'm calling sine the inner function, what's the outer function in this composite here?
Is it sine squared?
Right, but what's the outer function? In other words,
t is
no. This function here, it takes you from any x value to sine squared t, doesn't it?
Yeah.
Now, oh, I wish I knew what the excuse me a minute. Oh, there we are, new toolbox. And what's that? Is it going to tell me what the shortcut is? Okay, anyway, I'll have that. All I want to do is this. Get it out of the way. Right. So the function that takes you from x to sine squared, t to sine squared t, I mean x, do I?
No.
I don't, do I? The function that takes you from t to sine squared t is in 2 stages, isn't it?
Yeah.
What's happening first? I think sine is happening first.
Yeah, sine.
And then, so we get sine t here.
Is it sine again?
Is it though? What's happening to get you from sine t to sine squared t?
You're squaring sine.
You're squaring it. I could put x squared there, like on a calculator button, meaning square anything. Yeah?
Yeah. Yeah.
So when I ask for the outer function, I mean the later function, the subsequent function, which is?
X squared.
Squaring.
Yeah, squaring.
All right. So I'll generally look at a composite like that and think of it as having an inside and an outside.
Yeah.
You could think of it as, you know, a first stage and a second stage. Now, the chain rule, which we've alluded to here, usually it's written in terms of u, isn't it? dy dx equals dy du, which means differentiate the whole thing with respect to the whole of the inner function. In other words, think of that there as just being blob squared. And blob squared will differentiate to what in terms of blob?
It would just be blob.
Well, what's x squared differentiated with respect to x?
It would be 2x.
2x. So blob squared is
Blob x. Wait.
no,
Blobs. It would be 2 blob.
2 blob. Okay, but the chain rule says do that, differentiate with respect to blob, but then you must multiply by du dx, which means the derivative of the inner function, doesn't it?
Yeah.
So here we're going to get what? What's the derivative of the inner function?
Cos t.
Absolutely. And the blob was?
The blob was sin t.
Sin t. So 2 sin t is dy du, the derivative of the inner function with respect to the inner function.
Yeah.
Okay, so the whole thing is 2 sin t cos t.
Yeah.
Can we simplify that?
So sec is 1 over
Yeah.
1 over cos. 1 over cos. So
Yeah.
So it would be 2 over cos over 2 sin t. And
Yeah, I think the 2's are going to cancel though, aren't they? So we don't
yeah.
worry about them.
So you have
The
1
rest
over
would be 1 over
sin t.
So if what we've got on top there is 1 over cos squared,
Yeah.
so what have we got down here?
Sin t cos square t.
I mean,
1 over
for example, what's 1 over x squared over yx?
It would be it'd be yx over x squared.
I'm not buying that. I think it would be 1 over x squared
Times
by yx. Okay, which is like 1 over x squared times what?
1 over yx.
Yeah.
So okay, yeah. So then it would be x cubed y.
Yes. Do you see how this is a bit similar?
Yeah. So then that would make the cos cubed t.
Yeah. Right. Okay. So we could also say that's like cosec t times what?
Cosec t times sin t.
No, the 1 over sine t is giving me the cosec.
Sec. So cosec times sec cubed.
Well done. That's true. I mean, I'm not sure if either of those, is best. The tangent to c at the point. Anyway, we've got dy dx in terms of t here.
Yeah.
I mean, you could just cancel the 2's and give them that. That would be fine. But that is that. But you might prefer to express it as cosec times sec cubed. I don't know. I mean, it's a weird one. In fact, I've said it's weird. I just want to check it's correct. 2 sec squared t over exactly that. So that's fine. Yeah. Now the tangent to c at a particular value of t there cuts the x-axis at the point P. Find where it cuts the x-axis, in other words. So find an equation for the tangent to c for this value of t then. So we know it's going to be what form of equation?
Is it parametric?
No, we're going to just have a Cartesian equation, a normal equation for the tangent. In other words, it's a straight line, so we're thinking in terms of y equals mx plus c.
Yeah, y equals mx plus c.
Which we know then, if we put this value of t into here.
Yeah.
And here, of course. Okay, so taking each in turn, what's sine of pi over 3?
Sine over...
Pi over 3, which is what time on the clock is pi over 3?
Okay, so we start at 3.
Yes.
Up to 9 would be 1. So...
Yes, that's right. Sorry. Yes.
Is it 1 o'clock?
1 o'clock, good. And then we should be able to soon see, sorry, we've got a bit waylaid there. So going from 3 o'clock, as you say, up to 1 o'clock is pi over 3, because 9 o'clock would be the whole of pi.
Yeah.
And we want to know the sine, and in a minute, the cos of that angle there.
Yeah.
So what we do, isn't it? We think of that as a grid. I missed that point there, didn't I? Completely. Right. So thinking of that as a grid, so we get the sine and cos of the angle here. What is it, t? No, it's not. Yes, t is an angle. This parameter of the equations is an angle. We can call that t. And 1 o'clock would represent pi over 3, quite right. And did I talk about thinking of the vertical and horizontal axes as
X and Y, or sine and
y,
cos.
or sine and cos and sine. So first of all, well, actually, cos is easier, isn't it? Let's do cos of pi over 3 first, because we can see that the cos value for that value of t is going to be right there, which is what? What's this? What's this cos value there?
Is it 1?
Well, no, this is the unit circle. So the point is the radius of the circle is 1. So here's 1 on the cos axis.
Oh, yeah.
The cos of 0 is 1, isn't it? Because 3 o'clock is 0.
Yeah.
So we guess that this might be what? This one here.
1/3?
Your reasoning there has to do with the angles. We're cutting 90 degrees into 3 pieces. But notice that on a clock, next time you look at a clock, notice all the lovely equilateral triangles.
Yeah.
And there's a lovely equilateral triangle going from 1 o'clock to 3 o'clock to the center.
Yeah.
In which case this point here is precisely where? So like an XY grid, the cos sine grid is, here's the origin. And yeah, this is 0.5 or a half is the cos of pi over 3.
Yeah.
Okay. And sine, that's not quite such low-hanging fruit. We'll have to work out the height which is going to be the sine coordinate of this point, pi over 3. So the cos coordinate is a half. So we know the base of the right-angled triangle is what? The right-angled triangle I'm pointing to. I'm thinking that's going to be hard on a phone, but
Yeah, I can see that.
yeah. So that's a half, the adjacent.
Yeah.
The hypotenuse is what?
The hypotenuse would be
It's the unit circle.
okay, so it would have to be, would it be 1?
Yes, it's the radius of the circle.
Yeah.
So the hypotenuse is a half. Sorry, no, the adjacent is a half. The hypotenuse is 1. So what's the opposite side which we need for the sine? And of course,
Yeah.
the length of the opposite side, by the way, is just going to be the sine because the hypotenuse is 1. Opposite over hypotenuse will just be the opposite side, which is why we can think of the vertical axis as the sine axis.
Yeah.
So do Pythagoras for me to find the height of that point on the circle at pi over 3.
Okay, so it would be, to find the height, it would be 1 squared take away a half squared,
Yes,
which would be, is it 3/4?
that's right. But
And then you have to square root that.
we do for Pythagoras, yeah. Getting?
Square root. Is it √3/2?
Yes, it is. The sine of pi over 3 is √3/2. Notice it's also the sine of what angle here at 11 o'clock? What angle is it? Yep.
So, I'm not sure.
In degrees, well, I mean, it's just another third of pi, isn't it?
Yeah.
I mean, degrees
So
is another 60 degrees. So it's
60 or
120 degrees or 2 pi over 3. I'm just saying, by the way, these results that you get here on the unit circle, there aren't that many of them. They're repeated at other places. Plus or minus, perhaps. So this comes out as the 1 over sine t cos cubed t. We've got sine t, we agreed was what?
3/2 pi. No, 3/2, sorry.
You've lost me. Sine t?
Sine t.
Oh, no, you haven't. Sorry, I shouldn't have got lost from what you're saying, but you said it. All right, when you corrected 3/2, what did you say?
I forgot what I said.
Let's go back there. It never hurts to go through the Pythagoras in your mind.
Yeah.
You've got
So
a half here, you've got 1 there.
The height is √3/2.
Say again?
The height is √3/2.
√3/2, that's right. So we have got √3/2 times the cube of what?
Cube of cos t, which is it was a half.
It was just a half, wasn't it? It was halfway along from the center of the circle to the circumference.
Yeah.
So cube it, and you've got
0.125, which is an 8.
good. Are you getting into decimals mentally or using a calculator?
Mentally.
Fine, yeah, okay. But you'll find fractions should be friendly.
Yeah, I realize.
Yeah. So what does this simplify to? On the bottom, what have we got?
We've got √3/16.
So 1 over that fraction would be what?
1 times the reciprocal of that. Wait.
Yes.
Yeah.
I mean, and the reciprocal of that is? What's the reciprocal of √3/16?
16/√3.
Sorry, so, well, exactly, yes. So this is going to be our gradient at the point t. That's the gradient of the curve at the point t. It'll also be the gradient of the tangent at the point where t, well, I say the point t, I mean the point where, the point P, isn't it? No, no,
Yeah.
no, it's not, sorry. The point on the curve where t is pi over 3 doesn't have a name. We shouldn't call it pi over t. But anyway, y equals, therefore, our m value is what? What's the gradient of the tangent at the point P? No, not the point where t. Sorry, no?
The gradient.
How do we know the gradient of the tangent at any point on a curve, including this curve?
I forgot. It was. My mind's just gone blank.
Don't worry. I mean, why did we differentiate? Oh, because they told us to. But we probably would have done that if we wanted to know the gradient of C at any point on the curve, wouldn't we?
Yeah, yeah, yeah.
Differentiating is how you find the gradient, isn't it?
Yeah, yeah.
Well, we differentiated, and then we found the gradient at the particular point where t equals pi over 3.
Yeah.
So we found the gradient at a particular point, and that's going to be the gradient of the tangent at that point, isn't it?
Yeah, yeah, that is.
Well, we're trying to find the equation of that straight line, and we know it's going to be in the form y equals mx plus c.
Yeah.
So we know the m value, the gradient is going to be?
Oh, it would be what is it? It was
What was
16 over 3. 16 over 3.
16 over root 3, good. Yeah. So we know we've got y equals that fraction times x plus c.
Yeah.
And then how can we also need to know the y-intercept, c value. How can we set about finding that?
Um.
What do you look for when you found the gradient of a straight line? You say, okay, well, is there any particular point on that straight line that I'm aware of, that I have the address of?
Do you make x equal to 0 and?
Not yet. We can't. We need a point where we know both coordinates.
Okay.
So this curve, whatever it looks like, I've no idea whether it looks anything like that. I suspect not. I'm just drawing that as a generic curve to think about the tangent at that point.
Yeah.
But what points do we know about on the tangent? Well, I think our only candidate is the point where it touches the curve.
Yeah.
What are the two coordinates of that point there? Do we know?
Is it 2 tan t?
No. Yeah, the y coordinate is 2 tan t, yes. And the x coordinate we can find similarly. Because what we do know about this point isn't actually its xy coordinates, but we do know its t value. So we can use the parametric equations to find the x and y, can't we?
Yeah.
All right, x value first, perhaps. So the x value is going to be the square of the sine of t. So let's go through that. What's the sine of pi over 3, did we say?
Was it
root
3 over 2? Root 3 over 2?
Root 3 over 2. Make sure you've got the right one there. Yes, because it's the opposite side, the vertical coordinate of this point on the circle.
Yeah.
Root 3 over 2. Square it.
3 over 4, 3 quarters.
Yes, because that's how you got there, isn't it? By square rooting 3 quarters. So square it back to 3/4. And the y value, 2 tan t. Well, we haven't talked about the tan of this angle t.
Yeah.
But can you work out what it is? Because you've got, assuming the hypotenuse is 1,
Yeah.
which we do in the unit circle, we've got the opposite side is √3/2. We've got the adjacent side is?
A half.
So can you work out the tan, opposite over adjacent?
So it'd be √3/2 times a half.
Ouch. Socrates defines tan as?
Opposite over adjacent.
Yeah.
So that means a half divided by, √3/2 divided by half.
Yes, except √3/2 came out as 2/√3 or 3/2, didn't it? But you meant √3/2 divided by a half, yes.
Yeah, yeah.
So what's √3/2 divided by a half, or over a half?
So √3. Okay, so 2√3/2.
Yeah, but that simplifies, doesn't it?
2√3/2. I'm not sure how you simplify that.
What, 2√3/2?
Yeah.
What about 2x/2?
Oh, it would just be √3.
Yeah. In fact, notice that this situation here, I mean, it is just a case of cancelling, isn't it?
Yeah, yeah, yeah.
So, but only because of what happened later. I suppose it's not necessarily reliable. But yeah, tan of t at that point is √3.
Yeah.
So the y coordinate is?
The y coordinate is 3.
Ouch. Did you square it?
Oh, I mean √3, sorry.
Right, but y is given by?
So it would be 2 times √3.
Yes.
So 2 √3.
Doubling, not squaring. I don't know if that's what happened.
No, I meant √3, but I accidentally said 3, but then I forgot to times by 2.
Wow, right, okay. So, looking into it in a simple way, we do have the x and y coordinates of this point on the straight line now, don't we?
Yeah.
Right. So, how should we use that information about the point on the straight line?
But then it would be y equals 16/√3x plus 2 √3.
Not that simple, no.
Oh.
Why would you think? Oh, because that's the y value of that point.
Yeah.
Well, if we had some reason to know we were on the y-axis, then yes. But then the x value would be 0, wouldn't it?
Yeah.
Which it's not, is it?
Use
this information to find out what c is.
Is it the? Is it the y take away y1? No, wait.
Well, yeah, you can. Yeah, I mean, I'm not a fan of that version, but there's nothing wrong with it. But I would just say the y value. I'm going to say, for example, because here we're being more general, aren't we? Y is so many x plus this unknown constant for all values of x and y. But now we're saying, because we know a particular pair of x and y, let's look at that example. For example, 2√3 equals 16/√3 of how much?
16/√3 of is it 3/4?
Yes, the x value at that point.
Yeah.
See what we're doing. Plus c. Now we can solve for c, can't we?
Yeah.
So c equals,
C equals 48 over 4 root 3.
yeah, let's, are you using a calculator there?
No.
No, good. But in that case, let's do even better and cancel where we can.
Okay.
So first of all, let's write c and
Okay.
then say, okay, so it's 2 root 3 minus all of this stuff, which we'll write more simply by thinking, well, of course, 16 over 4 is... So we can cancel some of the 16, can't we?
Oh, okay, yeah.
We can cancel
16
all of those 4s in 16.
Yeah, so that would be 4, yeah.
That's just a
So
4. And 3 over root 3 cancels to... What does 3 over root 3 cancel to?
3 over root 3.
What does it cancel to?
1 over root 3?
No. It wouldn't, would it? Because you're leaving the denominator alone then, aren't you? And changing the numerator. But surely 3, we
Oh,
think of it as root 3, can't we?
yeah.
So the
So
whole
it just
thing
be root 3. Would it just be root 3?
would just be root 3.
Yeah.
So the 3 over root 3 cancels, and
Yeah.
16 over 4 cancels to 4. So we've got 2 root 3 minus
4 root 3.
4 root 3, which of course is
Minus 2 root 3.
good. So now we can state the whole equation just for our own benefit. I haven't asked for it, but we're going to use it obviously to find the x-intercept. I think it was the x-intercept, wasn't it? So y in general equals, because we got more specific here, didn't we? Now we're going more general again.
Yeah.
16 over root 3x minus 2 root 3. And now, of course, another example would be the x-intercept. Was it the x-intercept they want? Yes.
Yeah.
Yeah. So, for example, 0 could equal that at the x-intercept, and we just solve for x.
Yeah.
What do we get?
We get 2 root 3 over 16 root 3. No, wait.
Yeah, probably actually. Yes, sorry, that is a perfectly good way of putting it, isn't it? No,
Yeah, 2 root 3 over 16 over root 3. So I'm saying 2 root 3 divided by 16 over root 3.
yes, and dividing by 16 over root 3 is like doing what?
Times in by root 3 over 16.
Exactly, that's the way to put it, yes. So x is going to be 2 root 3 times root 3 over 16, yes.
So that would be 6 over 16.
Yes, good. In other words,
3 over 3 over 8.
that's it. That's what they wanted, the x coordinate of the x-intercept.
Yeah.
Okay.